7.3 lesson. So if you put electricity into seawater, what you've got are three things: water, chlorine ion, and sodium ion. And then four things could possibly happen because water could go either way. Chlorine ion could possibly oxidize and give up electrons. I mean, I guess it could happen. And then sodium could accept electrons, right? And turn into sodium charge 0. So water could go either way. So on the oxidizing, let's find the reduction value of the chlorine and turn it around, change the sign because the reduction was positive, but we're oxidizing it. So we get a negative value. The thing to remember with water is that if it oxidizes, it's going to be giving up the electrons from the oxygens, which forms elemental oxygen. So you need to go find the reaction that has elemental oxygen involved. And of course, they'll list it as a reduction, but we're going to say it's oxidation. And then we change the sign here. So we go and find the reduction value for sodium. Don't change the sign. And if water gets reduced, if anything's going to accept electrons, it's the H's, which is going to form elemental hydrogen. So find that version of the reaction. In real life, if you put electricity to seawater, what you get is the easiest reaction. So if we take up any possible pair from here, one of these and one of these, we're going to get a negative value. But what's the easiest negative value to overcome? What's the least negative addition answer you could get? Well, it's going to be using the least negative values. So it's going to be this one because that's less negative than that, and that's less negative than that. So we're going to add this and that. Here we go. And here's the voltage you need to overcome to get the reaction to happen. So it's resisting the reaction with this much, so to speak, electrical pressure. And so your power source has to be greater than that volts to get it to go. On two, we're talking about silver plating. And so I've discovered that some kids don't even really know what the question is talking about. We're going to deposit silver onto something else. Okay. We're going to take a ring, for instance, and we're going to plate silver on top of it. It's something much cheaper like copper or something. And we're going to deposit silver onto it so that it's coated in silver. And then we can polish it up and we can sell it as cheaper jewelry, right? More affordable jewelry because who's looking inside the thing anyway? So we're going to do this by electrolysis. What we're going to do is make the ring be the cathode. Now go back and do a bit of review, but at the cathode, the solid metal is formed and the anions are attracted to the negative charge of the electrode, and they come over and they pick up electrons and they stick themselves to the electrode. We're going to make the ring be the electrode, and what we're going to get is a coating of silver metal on it. So this also is something that you need to know. They almost certainly would build this into almost any test, that at the cathode, the mass is gaining. That's where the solid metal is being created. The cations are migrating over to that electrode because it's receiving electrons, so it's becoming negative, and they're going to pick up electrons and stick to it. This is what we're going to have happening. That's aqueous, that's solid. And so what you get is your cathode electrode being coated in the new metal. Now, when we introduced this whole topic, it was coated in the same metal, just more of it, but we're going to change it out so that our electrode is not made of the cation element. So what we're going to get is an interior of something else, say copper, coated with the silver. Now you might want to do some calculations. If you run this cell for this long at this current, how many grams will you be using up? Because of course, more silver is more expensive. And this is a bit of a slog. I'm going to try to explain it in piece of logic here. So I want to know how many grams it would be. Well, we've done moles to grams many, many times. So if someone would tell me the moles of silver that were deposited, I could tell you how many grams pretty easily. So how many moles is it? That's the hole in my information right now. The trick here is that the current of the cell isn't measured in moles, it's measured in coulombs. So what you're going to do is say, actually, let's take a step back. And if someone would tell me the coulombs, I could take Faraday's constant and convert that to moles of electrons. And the reason that works is I know, looking at this cation, that for every one electron that gets fed in, I can deposit one silver atom. So if you feed me 1,000,000 of these, I can deposit 1,000,000 of those. If you put in a mole of electrons, you can deposit a mole of atoms. In this case, it's 1-to-1. It's one silver atom for every one electron. Now, it might be 2. Of course, this could be a 2. If that was a +2, you'd need 2 electrons, right? So this could be 2 or 3. So we wanted moles of silver, but that's not going to happen. What we know is stuff about electrons. We know the amps that were used. That's amps. That's amperes. We need to know that. Capital A as a unit is amps, and an amp is coulombs per second. So what we have is information that it does involve the number of electrons. It's just that we need to convert it from coulombs to moles. And this is one of those exercises, I think, in just making everything flip until it all cancels out right. So I would write down, I want grams. That means I'm going to do moles to grams. And that kind of sets you up here. And then you say, well, what I need is moles. And Faraday's constant converts between moles and coulombs. And the extra trick there is realizing that really what you know is 1 mole of silver for 1 mole of electrons. So it's legitimate to put the moles of electrons down here. And that could be 2 or 3 or whatever. And then what we know is amps and seconds. An amp is a coulomb per second, and they think you know that, and I think it's in the table of constants and formulas, but we can't flip back for everything. So here we go. If we know seconds, we can cancel out the seconds inside coulombs. Faraday's constant will cancel out the coulombs from there. That gives me moles of electrons. Now, I know that it's 1 electron in for every 1 atom deposited. So that gives me moles of silver, and then I convert to grams of silver. I would cover that over and try to reason your way through it. It might take a few times, but they get to ask something like this. Read through number 3, except I'm going to take issue with the word decomposition. I'm probably going to change this to formation of metal X at the cathode, because what we have is a molten salt. So we have X element as the cation with some unknown anion. So we've melted that. Now, what they think you know is that we have a bunch of X plus and something minus running around. There isn't water, okay? But we're going to put electricity into this. If you give this thing extra electrons, what's going to happen is that the X cation is, see the cations, the possible cations, are going to go to the cathode and stick and become X charge 0 metal, actual metal, solid metal. Now, if you knew how many electrons it took, you could figure out the charge. Just for pretend numbers, if you knew that it took 200 electrons to stick on 100 X cations, you'd know it would take 2 electrons per cation, and that would mean it was +2. So what is the charge? What we want is the ratio. Remember, we essentially did a ratio there of 200 to 100. So what is the ratio? We basically did a ratio of 200 to 100. So what are the numbers? Well, we know this number because they told us it's 0.25 moles. So what we want is a ratio, but we want to put electrons up here, except this is a mole, so I want this to be in moles of electrons, but electrons aren't usually measured in moles, so we're going to have to convert it with Faraday's constant. So how many electrons is that? Well, we know the time, and they kind of think you know that an hour is 3,600 seconds, or you could work it out. And an amp is a coulomb per second, so that's 10 coulombs per second. That cancels out the seconds here if you do it like this. And then you have number of electrons. You can convert that to moles of electrons, and then you have a ratio. And this, when I did it, came out to something really close to 0.75 anyway. The easy part about this is that you can't have fractional electrons. So if you get 0.74286 or something, it's 0.75 because you know you have to get a whole number. And so it took 3 moles of electrons per mole of cations. So it must have been charged positive 3. 4 is kind of a layup. If this is going to take more electrons per cation to deposit it, then it's going to take more time. 5 might kind of seem like an impossible question. It's a little convoluted, but we know that the metal is attached to 3 chlorines, which means it's a positive 3. So if we can count the electrons, we can divide by 3 to find out how many cations we used. And what we're looking for is the metal. Well, what identifies a metal? Not the charge, but you know what gets really pretty darn close? If you can find the molar mass. So we know how many grams were deposited. If we knew how many moles were deposited, we could do grams per mole. And that would give us the molar mass. And then we could look on the periodic table. So we already know the grams. What we're looking for is the moles. So what we're going to do is take the amps, multiply by the time to get the number of electrons, acceptance in coulombs, convert it over to moles of electrons, and then say, but I know it takes 3 electrons every time you do it, so I have 1/3 as many as that in moles of actual cations. Then I have the moles of cations that were used, or moles of atoms that were deposited, same thing, and I can do grams per mole, gives me a molar mass. I can look up, oh, it was scandium. On 6, what they don't exactly say, but what they mean is that they're going to put in both an anode and a cathode into the molten salt. Okay, so you're going to get an oxidation reaction and a reduction reaction. And it does kind of only stand to reason what's going to happen here. I mean, K plus is not going to go to K double plus. So the Ks are going to get reduced. They're going to receive electrons. The Fs are going to give up electrons, they're going to get oxidized. They're going to form the elemental diatomic state of fluorine. So how much fluorine would you get? Well, kind of fundamentally, we know that there are 2 electrons involved for every 1 fluorine diatomic molecule being formed. The circuit has to complete, so the electrons going in is equal to the electrons coming out. So we'll just borrow these numbers when we're discussing the fluorine. So if I knew the moles of electrons, I could say, well, I just get half as many fluorines, right? So what is the moles of electrons? Well, I don't have moles, but I do have amps, and amps contains number of electrons. It has it in coulombs. So if I take the time, and 1 hour is 3,600 seconds, so that's 7,200 seconds, and cancel out the seconds, I get coulombs. That's groups of electrons, just in a different measurement. Faraday's constant will convert that to moles of electrons, and then I can say, but I only get half as many fluorine molecules as I had electrons used. So what would be the volume? Well, take PV equals nRT, rearrange for V. We just figured out N moles of fluorine molecules. Pick the right R so that it matches the atmosphere that they gave you. Convert your temperature to Kelvin. There you go. How much potassium would be formed? Well, it's 1 electron for every K, and we just found the moles of electrons, right? So it's that many moles of K, and then we can convert to grams of K. On the free response, we have this reaction, and we know the grams produced of aluminum, apparently. What's the moles of electrons that must be transferred into the cell? I know it's going to take 3 electrons for every 1 atom formed because we know aluminum is a +3, plus you could figure that out from the charges here on the oxygen. So I can take the moles of aluminum formed and then multiply by 3 to get the electrons that were needed. So let's just convert the grams of aluminum to moles and then multiply by 3 using this ratio to get moles of electrons used. To get time, What you need to remember is that inside an amp is a coulomb per second. There's time inside amps, and they just handed us amps. So essentially, they just handed us seconds. I just need to cancel out the coulombs. And what I'm going to do is convert my moles of electrons to coulombs using Faraday's constant. Then that coulombs will cancel out this coulombs and give me seconds. For D, I think this answer is a little misleading right here. We must be in the liquid state because the aluminum needs to move so it can go to the cathode and pick up electrons and get reduced. However, the oxygens move, but they do not get oxidized. If you go up to the original reaction at the top, they stay an oxidation number of -2, so they didn't get oxidized or reduced. In fact, what happened is they caused the carbon to get oxidized because the carbon goes from charge 0 on the left to charge +4 on the right. On this part, you don't even, in a sense, have to read very carefully. You know, what's the question? What's the E standard for the formation of the products? Well, it says it's just placed in there. This is not electrolysis. We want a positive voltage, and something has to oxidize. They can't both be reduced. So clearly, this is the number we're going to flip. We need a positive voltage. Something's got to turn around. We have to change one of these signs and get a positive in the end when we add these up. So it's that one that's going to change, which flips this whole thing. Then, though, we do have to remember that this is using 3 electrons, and that's 2. So we'll multiply this line by 2, everything in it, this line, everything in it by 3, shove them together. The electrons cancel out, and we get a net ionic or overall reaction, kind of same thing, and add up the flipped sign, remember, the change sign here, and we get the new E standard voltage. So what's delta G standard? Well, I just found E standard. This is E naught, E standard. And so I do have enough information to go find delta G standard. If you put in E standard, you get G standard. You might not remember this equation, but it's in the reference pages. Also, I just found out that this is 6 electrons, isn't it? Faraday's constant is a given, and you can put in volts for this if you want. They can't charge you off for that. And just multiply at that point. Remember, though, that there's a negative sign. If you give a positive, I bet they don't give you the point. You've wasted your time completely. You need joules per mole, and that's got to be a negative. When this reaction happens, the voltage potential standard is a positive number, but the delta G standard free energy change, the change, delta is change, is a negative because the energy came out of the reaction.